All right, everybody. So I think we'll get started now. So thanks again for joining this injection molding material selection webinar presented by Quick Parts. So the speakers that will be presenting today will be John Sidorowitz, he's our VP of Sales, and Glenn Miller, our Senior Tooling Engineer. John has many years of experience, over 15 years in manufacturing and sales leadership, project management, and customer support. Then Glenn Miller has over 25 years experience in injection molding. My name is Matt. I'll be presenting too as well today a little bit, so those will be the speakers today. And with that, I'll hand it over to John and Glenn to get started with the agenda.
All right, thank you, Matt. This is John Sidorowitz. Thanks for joining this afternoon. Kind of go over the agenda quickly and then jump into things. And if you guys are familiar with Teams or not, there's a Q&A button at the top, maybe off to the right. So if you got any questions during the webinar, feel free to submit those, and we'll get to, or try to get to most of those at the end. If something comes up maybe during a slide or two that we can add in, we'll pick up that question there. So the agenda for today, just understanding the basics, pros and cons of injection molding materials. What are the materials, what's in the types, I guess. We're going to review some base materials or more of your common type materials. Look at those, the pros and cons, where you would use them and whatnot. And then kind of discuss cost saving tips or kind of the process for, selecting a material for your part. Next slide. All right, so we're just going to get to general material properties. Next slide. So when it comes to plastic, there's really two main types of polymers: thermoplastics and then thermosets. At Quick Parts, on the injection molding side, we only run thermoplastics. So a thermoplastic essentially is a polymer that can be formed and then melted and then reshaped again. Without really losing their properties. That's why it's highly recyclable. And you're going to see it in just about everything. So most of your injection molded products are going to be made of some sort of thermoplastic. And these are your ABSs, your nylons, your POM materials, polycarbonates, so on and so forth. The pros with them. The recyclability of them, resistance, they're flexible, lightweight. Cons, you can only get so much temperature resistance with them. Some materials can be costly, and they may not be as strong as compared to a thermoset. Thermoset materials, a little bit different. Kind of they're one and done. Once that material sets, you're not changing it. So you're going to see a lot of thermosets in electrical applications, aerospace, even some construction applications as well. And this is due to its, heat resistance, the durability, dimensional stability. Like I said earlier, you can't remold it. You can't really recycle it. And it can be brittle. And the process to mold these parts is a lot longer than injection molding because it typically involves curing, molding and curing and all that. And some example thermosets are going to be, two-part epoxies, polyesters, and phenolic materials. Next, we've got a couple types of polymers. Amorphous versus crystalline. So crystalline polymers or semi-crystalline have a highly ordered molecular structure. So you can see off to the left, the top left, and then kind of the bottom, the semi-crystalline. Everything's aligned with that. So there's high order. Once you shoot that part, the structure of that part is going to be, aligned like that. So what does this get you as far as characteristics? You're going to have high resistance to stress cracking because everything's aligned and nicely tight knit. You're going to get poor dimensional stability. So, depending on how everything's aligning, you may get shrink in one direction more than the other. But it does provide excellent chemical resistance. And some example materials you see there are polyethylenes, polypropylenes, nylons, PETs, and acetyls. On the other side, amorphous materials, they really lack that ordered structure that we have in crystalline materials. And you're usually going to find these with flexible or transparent materials like polycarbonate or polystyrene, and even ABS. Like I said, usually transparent materials, you're going to have that structure. You'll have better dimensional stability. You're going to have lower shrink rates. Like a polycarbonate ABS has a 5,000 shrink rate versus maybe a nylon that's a crystalline that has a 15,000 shrink rate. And then just better impact strength as well with the amorphous materials. I'm not going to go through this chart in its entirety. I mean, we'll make this available to everyone that's on the call or at least signed up to be here. There's a lot going on here, and it's just kind of a guide to help you kind of pick materials or kind of see where things fall on the scale. So we've got a temperature scale on the left. And in the middle, we've got the kind of materials pyramid broken down between the amorphous and crystalline materials, and then kind of built up from your standard resins to your engineering grade to your advanced engineering grade to your really high-end materials like your peaks, your ultims, and those type materials, which are going to have really high temperature resistance. But yeah, I'm not going to really break through each one of those, but we kind of break it down by the materials on the right and left and kind of go through there. So obviously, starting at the bottom are going to be your cheaper materials, and as you go up that pyramid, that price per pound is going to increase. All right, now we're going to move on to just some common materials that are out there, and kind of talk briefly on them. And again, if you have any questions or anything, please feel free to submit them via the Q&A button at the top.
Thanks, John. Again, my name is Glenn Miller. John and I will go through some of the more common materials. We'll start right here with ABS. We'll go through some pros and cons here real quick. ABS has good impact resistance. It's tough. Great for a part that needs to have a certain kind of rigidity to it. An ABS allows for good adhesion with some kind of coatings, metal coatings, things that are used for, like a certain kind of shielding that you might need for your components. Really good processability. Appearance is very good. Takes polish, takes texture very well. Few resins that we do use. There are more, but these are some more common ones. Lustran 348, a Bay blend, T65. That's kind of a blend of ABS and PC, polycarb. Some cons to ABS, poor solvent resistance. So if this is anything that's going to come in contact with any kind of oils or other kind of chemicals, it's probably not the best option for you. They're not a real good insulator. There are other materials that are. It melts very easily. So again, that would go back to probably wouldn't want to use this for a application that has a lot of high heat. Some of the applications, a lot of housings like your PC and your computer, more times than not, those are made out of an ABS material. Same with small appliances, any of those plastics that form a lot of the housings, a lot of the interior trim on automobiles, and certain components of medical devices as well.
All right, polycarbonate or PC is another very common material that's out there. It's more known for, its clarity. It's a transparent material. It's high impact resistance. It's got decent flammability performance depending on the material or the actual grade. Similar to ABS, the dimensional stability is good, and it's got decent chemical resistance in some of the blends. Similar to ABS, another common material is a blend of PC and ABS, which is going to kind of marry the two materials and give you the best of both. Cons to polycarbonates, it's not really going to hold up. It's going to hold a little better than ABS to solvents. Going to be more subjective to stress cracking, degrades if not processed correctly. Higher processing temperature, and if a non-UV material is exposed to UV light over time, that part will yellow. If the parts sit out in the sun or just exposed to UV, it'll yellow after time. Some common materials that we have in the top right, more of the macrolons, 2405, 2407, 2458. There are medical grades as well. Then we list some of the blends, which is the PCABS blend that Quick Parts offers is the T85. But you're going to find PC, automotive headlights I'm sorry, Glenn? I thought you were saying something. It's a common material. You're going to find it, telephones, some of your electronics equipment, in your vehicles. But yeah. Next.
Next up on our list is nylons. We use quite a few of these here at Quick Parts. Some of the pros, high temp resistance, not necessarily for long periods of time, but over a short term, those materials work very well in areas that get heated up. Really good chemical resistance. So if you've got something that's going to, again, the previous materials did not, but if you have an application where this is going to come in contact with chemicals, this is more of the type of material that you need to look at. It's tough, so it resists abrasion, scrapes, scratches, little tougher than some materials. You can drop it. Chances are it's going to bounce rather than break. So good material for things that require a little durability to them. Some of the cons, they do absorb moisture, some more than others. They do require UV stability, or application that would require UV stability, excuse me. Strong acids and bases as well. High notch sensitivity. Common nylons, the Zytels, the 101s is a very standard brand we use, as well as the 70 G13 and G33 glass filled. Applications, a lot of automotive components, bearings, any kind of connector, gears. These are items that need to be strong, need to handle wear and tear. A lot of consumer products, many industrial products, too many to actually list here.
All right, next, polystyrene. Very similar, I wouldn't say very similar, but similar to polycarbonate as far as clarity goes. It takes high gloss well, like polycarbonates. FDA grades available. It's a lower cost, good dimensional stability, and good rigidity. Cons, it's not as flame retardant as polycarbonate. Again, poor solvent resistance. Parts can be brittle, more brittle than a polycarbonate, and still subject to stress cracking as well. You'll find polystyrene a lot in packaging, some housings, light pipes, windows, those types of things, even some containers and household goods.
Another material that we use quite a bit here be your TPEs, your thermoplastic elastomers. Some pros, low compression and tension set, easily processed in most instances. It's got good fatigue resistance, good tear strength, meaning it withstands a lot of abuse. Cons would be, flammability. Again, same with the one before. There are some flame retardant grades available depending on your application, and at that point, we'd suggest you get, obviously with any of this, you get in contact with a vendor technician and walk through what you need, and we can get you to the place that you need with these certain characteristics. Extensive heat aging causes severe change in mechanical properties. It just means it's, you leave it in high heat for a long period of time and it's going to break down. That's basically the gist of that. A lot of TPEs are a higher cost material. You really wouldn't use this type of material unless you had to. A lot of the applications we have down here, medical components, electrical, a lot of these items have delivery systems for fluids. This would be the kind of application that you would use a TPE for, a lot of household goods, sporting goods, and so forth. And next up on our list is additives. Glass additives. So several kinds of materials. You can add glass fibers to the material. They increase the strength, resistance to stresses, and can increase resistance to some high temperatures. We got three basic, I guess you call them classes. Glass bead. Dispersion is more consistent. The glass beads are consistent in their size and shape. They do provide a little better dimensional stability. The next type would be a short fiber. One of the more popular that we would use, a little more general, cost effective. It's very easy to process. Whereas a long fiber, better reinforcement and thermal resistance. They do get a little more finicky on the processing end of it. These fibers have to align themselves, and you have to process that a certain way with the proper temperature and speed and so forth. But yeah, here are basically your three different classes of glass additives. Some of the other additives that can be used, UV stabilizers, flame retardants. Certain customers obviously have an application where their part's going to be in a high heat area. They will, therefore, we'd recommend a material with a flame retardant in it. Impact modifiers, obviously the word impact, we're looking at something that withstands abuse. ESDs, anti-static, electrostatic discharge, additives can be added in for anything that, is in contact or in a component or an assembly that may give off a lot of electronic, static or other things. So these are the kind of the things you have to think of depending on your application, what you would want. Some applications you wouldn't need additives, but depending on your component, depending on your assembly and your product, you may need to look into some of these different additives. And next up is colorants. Pretty obvious what we're talking about here. Unless you want a black part or a white part or a gray, or natural. Sometimes this is the basic coloring that most materials come in. Colorants can be added to most natural colored materials. You can do what we call a color match, which is to, if you have something that is a specific color, it's kind of like painting your wall in your house and you put a dent in it and you have to go back and repaint a wall. You want to make sure that you get the color match to be what it was before that. So we can put you in contact, obviously with our help, to color match certain materials to get you the specific color you want. And then more to that point, some materials do come pre-colored at a certain color. Obviously, as you move down here with the more specifics on color, that does kind of add some cost because that material has to kind of be engineered and the color added. Here at Eccentric, we do all of those, and then there's a little note there, and that's more common for us is for a lot of the applications for our customers, we do a hand mixed color, just basically a certain ratio of the colorant to the resin. A lot of times that works just fine for certain types of colors. So we're happy to do either for you. And I kind of went over that, pre-colored versus hand mixing. More consistency with the pre-colored, obviously. It does come at a higher cost, like I mentioned. And hand mixed, again, it is just a basic ratio. We can get really close with that. It is literally hand mixed, batch to batch for each job. But the Quick Parts team is more than happy to help you with that. We can change that if we just determine that, after a first shot or as we run your job, you're not too happy with the color. We can then kind of direct you to go to a more pre-colored material if necessary. But we're always willing to work with you on things like that, of course.
All right. Move on to the next section. Cost saving tips for material selection. It's more of a guide than anything. But next slide, Matt. All right. So, obviously, when you're starting the design of a new product, the shape, the overall design, how it looks, and all that is obviously critical to it. But you have to also think about the environment it's going to be in, how it's going to be used, and take that into account into your design, because some materials you may have to design certain features in certain ways because you can get into standard or recommended wall thicknesses for materials. Some can do thinner walls versus others that require a much thicker wall. So things to think about, for your design or where your part's going to be is thermal. Is it going to be in the hot? Is it going to be in the cold? Is it going to be in both? Is it going to see sudden temperature changes? Is it going to be outdoors or somewhere where it's going to be exposed to UV? Or is it more of an internal part? Weathering resistance, again, is it outdoors? Electrical requirements, flame ratings, does this need to be an insulated type part? So those are the things you need to think about while you're doing your design. Because the problem runs in later on. Say you pick a material, identify a material, you build a mold, and you start shooting parts and find out that material is not going to work for that application. All materials have a shrink rate, a unique shrink rate, typically, within the family. Different grades can have variations of a family, but if you're trying to move from, say, something like a nylon to an ABS, or from a polycarbonate to a polypropylene, you're going to see a big jump in your shrink rates. And if you try to switch those materials or run those materials through that tool, you're going to end up with a different size part. Maybe bigger, maybe smaller. It may be okay in one direction and not another, just depending on the material. So it's very important to get that material selection up front. And Matt, if we can go skip the next slide and go to the 2 down. So once you can identify the environment, Quick Parts, we can kind of guide you, but we've got ties with a lot of the OEMs and largest distributors of materials. We can get you connected with a materials engineer, where they can take your requirements and figure out what may be the best material for you or for your project. And then if you want to skip back one. So, yeah, and when talking to, or consulting, material house or whatever it may be, want to make sure we're looking at easily or readily available materials when you can. Some of the specialty OEMs out there, they may guide you or push you towards exotic materials. The problem with those is they can have long lead times, high prices, and or high minimum order quantities. So, if you're in the prototype stage and looking to do a build of 500 pieces, a 5,000 pound run of material, you may not use in the end if that material doesn't work out for your product. And then kind of tying back to Glenn, try to stick to standard colors, where you can. Obviously, black, natural are usually your 2 standards, but there are a lot of materials now that are coming out with, other colors like reds, whites, greens, blues, yellows, and that. So that'll actually, help you save cost and time instead of getting that stuff pre-colored and or mixed. Yep, that was it.
Okay, so it sounds like a good presentation there, John and Glenn. Thanks again for that. I know we're running low on time here. I know we got a couple of questions coming in here, so we'll try to get to those before the end of this for sure. But just before we end, though, just a little bit about Quick Parts here. Been in business for over 23 years, over 100 million parts sold globally. A lot of experience in our operators and engineers. Happy to take on any complex projects you have, and are always evolving our technology to meet your needs here. And again, if you have any questions here that don't get answered during this presentation, feel free to reach out to us at sales@quickparts.com. We'd be happy to hook you up with an expert here that help answer any questions that you have. And I think with that, if John, you want to take some of the questions now that we have.
All right, we had one. Can you talk a minute about PA6 versus 6.6? I need something tough for my application for drop test resistance, and I don't need the stiffness. Unfortunately, I don't have that top of mind. Glenn, I don't know if you can comment on that or.
Not specifically, no. I mean, it really just comes down to how rigid.
Yeah, I don't have all the stats on both of those.
I mean, if you can provide us with more specifics, you can throw that our way. We can definitely have the team look at it and try to provide you with some guidance on that for sure.
Okay. Next, for hand mixing of colorants, how do you go about determining the ratio of colorant to resin? So our color house will send the version, the native material. So maybe it's a Lustran 348. We'll send that material to them. They'll develop the master batch for that colorant or for the Pantone that they're doing, and they'll actually determine the letdown ratio. And that's what we'll use moving forward with that colorant. Another one, any thoughts on replacing PPO glass filled with polycarbonate glass filled? Again, don't know the stats offhand. We'd have to look at and compare data sheets, but that's something we can definitely look at.
Yeah, I mean, you have to look at your shrink rates. You have to look at various issues, which again we can definitely guide you through that for sure.
Yeah. Couple more questions here. Does Quick Parts run any thermosets in injection molding? No, we do not. I mean, the only thermosets we really run is through our cast urethane process. where we use a two-part thermoset. Next question, can I use any additive with my material?
Well, it depends on the material and it depends on the additive. I mean, a lot of times, you know, if you want to use a certain colorant, or you should generally try to use the same base material for things like that. Other additives really depends on if you're talking about a UV stabilizer, it just really depends on the material itself.
Okay. Next one, what's the best way for me to try out different materials with the same design? I mean, in the past, what we have done with some customers that are, you know, like I said, if you're within the family, like ABS or like a nylon unfilled, your shrink rates are going to be very similar, you know, typically within 10%. But if you're looking to go across families like ABSs and nylons, things we've done in the past is kind of take an average shrink rate. And the customers, depending on the dimensionals, they try to make it work.
You know, same with
Glenn,
like TPUs, TPEs, TPVs, you know, the more flexible, rubberier materials. You can stay with, as John said, you can stay within that family. A lot of times the customer will want us to run, you know, 4 or 5 different durometers, stiffness on the material, which in general will work as long as we're maintaining the same basic shrink rate and staying within that family of materials. Yes.
What is the timeline in order to have a color matched? Well, I mean, if we're talking having a master batch done, it's typically, you know, 2 weeks to have that color developed, and that kind of runs in parallel with the tool. If there's a new tool in process, you know, getting pre-colored material, that's going to vary. It's going to depend on, you know, the material and the material lead time and all that. So that could take anywhere. I mean, I've seen from 2 weeks to 6 weeks. One more here. I work in the US and Asia. Are certain materials only available in the United States or Asia? Short answer, yes. I mean, most of the time you'll find the equivalents, both in Asia, you know, and the equivalent here in the US. And then you'll find both in both places. So it's really going to be material dependent. And I think that was the last one. Oh, no, we got one more. Can you do injection molding for a part that is 42 inches long? Well, maybe we would have to see the CAD and you know, take a look at it. But you know, if that's something you want to submit on quickparts.com, more than happy to take a look at it and see how we can help you. All right, I think that's it, Matt.
Okay, well, awesome. Thanks again, John and Glenn, and thanks for everyone for joining. Again, thanks for a little over here, but thanks for staying with us here. So I think with that, I think we'll let everyone go and get back to the day. And thanks again for joining us.
Have a great day, everyone.
Thanks. Bye.